Hi y'all. So I had already started these notes, and then I realized that I had forgot to start my video. So I was going to delete it and start over, and then I decided I would just talk through it. So we're moving into this concept of random variables. And so what happens is what we're going to do is we're going to take a random variable and we're going to assign that so that it takes on this numerical value. And so we're going to use the same probability rules that we've been using in Unit 4, but what we're doing now is we're going to turn this into these random variables. So this first question says, suppose we toss a coin 3 times. What would our sample space look like? So I went ahead and wrote this out, but if we're tossing the coin 3 times, we could do heads, heads, heads. We could do heads, tails, heads, all the way over to tails, tails, tails. And when we do this, every possible outcome we have 8 scenarios that we could arrange. So our sample set, total number of outcomes, would be 8. And the probability of any one outcome would be 1/8. Okay, so now we identify this random variable. So what we're going to say is let x, and this is an uppercase x, and we're just using x, but you can use other variables, y, z. What you're going to find is most often it's x. So let x equal the number of heads out of 3 coin tosses. So here's what we have. We have x equals 0, x equals 1, 2, 3. So what does this mean? X equals 0 means no heads in 3 tosses. So if I look at my sample set up here, this only happens one time. It happens right here. So the probability that that would happen would be 1/8. There's only one time when we don't get a head at all. And then the next one says the probability that we would get 1 head in 3 tosses. Well, that would happen here or here or here. So this would be 3/8. The probability of 2 heads, and if I look at the probability of 2 heads, I get that in this scenario, this scenario, and this scenario. So this is again 3/8. And the probability of all 3 being heads happens once. So I'm back to just 1/8. Now, because I've accounted for every scenario, if I add up my numerators, 1, 4, 7, 8, this is going to equal 8/8, which equals 1. So nothing here is new. This is all what we've done. What we're doing, though, now is we're assigning this random variable to have a value. And so this random variable x is the number of heads, and we say when we have no heads, 1, 2, or 3. So that is this concept of assigning a random variable. All right, so now what we're going to do is we have this frequency table, and if I look at this frequency table, this is my random variable, and this is going to be still number of heads. And if I look at my probabilities that we just found, we have 1/8, 3/8, 3/8, and 1/8. Now, what you're going to see is we're going to see distributions in this unit. And so if we create this distribution, so I have this value here at 0, and I know that I have 1 head. And then here I could have up to 3 heads. And then this one would be up to 3 heads. And then this one would be back down to 1 head. So this is what my distribution would look like, and we would use the same SOX rules that we had when we're describing this distribution, even though we're talking about one probability. So we could say that this is a symmetric distribution. I would even tend to say that it gives just this normal distribution. And this frequency table and the histogram represent a probability distribution. And that's really what we're looking at in this unit. So the probability distribution tells us the probability associated with each random variable. Now, we've seen this before because we've looked at probability or area under the curve. All right, so now what we're looking at is we're saying we've got one variable, and this one variable is going to give us this distribution. Okay, all right. So when we look at these probability distribution requirements, it says every distribution must satisfy each of the following requirements. So the first one is there is a numerical, not categorical, random variable. So in that case that we talked about just a minute ago, when we're talking about the probability of that, we're talking about the number of heads. We don't say X equals heads. We're saying X equals the number of heads over an outcome. So this gives us this probability, okay? And that's what this is. So we get this random variable, and each of the variables, X, has an associated probability with that. The sum of the probability in the distribution, so the sum of the probabilities in the distribution must equal 1. We just showed that on the other side. And then the last one is that we have this range of probabilities. So we have a range of probabilities, and what it looks like is 0 is less than or equal to probability of X, which is less than or equal to 1. And this probability of 0 says that it never happens, and this probability of 1 says it's certain, C-E-R-T-A-I-N, certain to happen. Certain to happen. Well, anyway, certain. Okay, so let's look at this. So here's our notation. Here's what this means. So the probability of X equals 2. So what it says is, what is the probability that the random variable equals 2? So if I go over here, the random variable equals 2 only at one spot, and that one spot is 3/8. What is the probability that the random variable is greater than or equal to 2? So now we have this value, but we also have this value. So we would have 3/8 plus 1/8, which is 4/8, which we could also say is 1/2 or 0.5, okay? And then what is the probability that X is less than 1? So it doesn't include 1, it has to be just less than 1, so this is going to be 1/8. So we're taking what we know with inequalities, and this is going to be really important when we get to distributions here in a little bit, but we're taking what we know with inequalities and we're looking at a table or a chart and we're just pulling those probabilities off and adding them together. All right, so what we have, and this is really what we're going to focus on for the remainder of this whole chapter, are discrete random variables. So remember, a discrete takes on fixed values with whole number outcomes. So we cannot have no decimals or fractions. They're all whole number outcomes. All right, now we do know that random variables can be discrete or continuous, but what we're doing today is just, actually this whole unit is just discrete variables. The random variables must be numeric in value. So we talked about this. So even though our results are head or tails, we described it numerically as a probability. So what this means is the mean of a discrete random variable is the mean outcome for infinitely many trials. Now, you've heard this said 1,000 times over, right? Everything that we're doing in stats means we're looking at many, many trials. It's not what happens if we toss the coin 3 times. It's what happens if we toss the coin 33,000 times, okay? So we think of this as the expected value, and this is a very important term here, the expected value. Because it's the average value we would expect to get if the trials would continue indefinitely, not what we expect in a single trial. So to find the mean, and the mean here would be our mean symbol, so this mu of x, x being our random variable, or the expected value, and that's going to be e of x. So expected value would be e of x. And in both these cases, we're dealing with this random variable of x that we've identified. All right. So if we look at this, just in terms of trying to identify this formula, if I have this variable x, I have x given one situation, or the second, or the third, or infinitely many possibilities, right? And I would have the probability that goes with this, probability that goes with this, and this, and this, and the probability of n terms. So what happens is when we're looking for the average, what we want is we want the value of our discrete variable, and we multiply that by the probability that's associated with that variable. And then we add this to the second discrete term. So when we have two terms, like this up here, so we have x is 0, 1, 2, 3. So depending on the context of the problem, and then multiply that by the probability of that taking place. And we go on and on and on, and we can use these three little dots to say x of n times the probability of n. If you have to show your formula for a mean, you have to show this whole thing. And you can use the ... on here. This is okay terminology, but you have to make sure you include your final part here. Now, this comes from our AP formula sheet, and what we have is the average of our discrete random variable is the expected value of that variable, and that's going to be the sum of all of the individual values times the probability of those individual values. So this is how it's worded on the AP formula sheet, but it's important to understand, and that's why I took the time on this, to look back and say, okay, this is really what we're doing when we're saying we take the sum of all of those individual values. All right? Okay, so let's put this to work and actually do a little bit of math. So if we look at this, it says Northwestern University posts grade distributions for its courses online. So it says the students in the stats courses received these different grades right here. So create a probability distribution for the random variable x, which represents the student's grade on a 4-point scale. So x here, it tells us that this is the student's grades. And if this is on a 4-point scale, I'm going to create a little table here that I have x and p of x, the probability of this occurring. So I would have my first term, my second term, so A, B, C, D, and F. I'll just say x of 5. Okay, so this would correspond to an A, a B, a C, a D, and an F. Okay, so what this says right here is that if this x1 is my A, and if I look at this, I get 0 points for an F, and 1 point for a D, and 2 points for a C, and 3 points for a B, and 4 points for an A. So if this is my A, I'm going to say that my represented variable is going to be a 4. And if I look up here, it says the probability of that happening right here is 0.26. 26% of the students receive an A. And if I look at my B is 42% of the students. And if I look at my C, this is 0.20 student percent. Probability, my D would be 0.10%, and an F would be 0.02%. Okay, now I'm going to add these up, and this probability needs to add up to 1. So let's just look at this really quick. And it does. It equals 1. So we know that these probabilities all equal 1. This is what I needed to do. So this probability distribution would look just like this. So now it says, find and interpret the probability of x being greater than 3 if x represents a randomly selected student in this class. So what this is saying is x is greater than 3. So this is going to be if they get a B or an A in the class. So I would say the probability that x is greater than or equal to 3 is going to be this value right here, which is 0.42. Plus the probability that they get an A, which would be 0.26. So probability then would be 0.68. So my interpret, the second part of this, is going to be the probability of a randomly, and remember, randomly is a super important word, randomly selected student in stats gets an A or B is 0.68. Now, here's what's important. It doesn't tell me anywhere that it's going to be an A or B. I know this because if we look up here, we know that it told us an A was 4, so a B is 3. So that's how I know that this is going to be an A or a B in my interpretation. Okay. Write an event: the student got a grade worse than C in terms of value of the random variable X. What is the probability of this event? So what I have here is the probability that the student got worse than a C. Well, it doesn't say equal to C, it says worse than a C. So the probability that they got less than a C would be X is less than 2. Now, you can also say the probability that X is less than or equal to 1. Now, here's how I know that I can do this. Because these are discrete and they're whole values, I'm not going to count this value here at 2. So technically the first thing that I'm going to count here is at 1. So if I said it's less than or equal to 1, it would include this value. Or I can say it's less than 2 and it doesn't include it, and it's still going to start with this value of 1. Okay? So if I look at the probabilities of this, it doesn't matter, either one of these. It's going to be 0.10 plus 0.02. So the probability that X is less than or equal to 1 is going to be 0.12. All right, so now this gets a little harder. So it says compute the mean, and we just figured out what the mean was. That was our U of X of the random variable X, and then interpret this in context. So U of X, so the mean of this random variable X is the same as the expected value of X. And so what I have here is, if I'm looking at the mean, I'm looking at my distribution of the value of X times the probability. So what I have here is 4 times 0.26 plus 3 times 0.42 plus 2 times 0.20 plus 1 times 0.10, and then I'm just going to write this down even though I know it doesn't matter. 0 times 0.02. So this is what this looks like. Now, if I plug this in my calculator, I have 2.8. So if I add that up, I know here that my mean is going to be 2.8. So in the context of this problem, what does it mean? All right, so here's my interpret. If many students, remember we just talked on the first page about how we need to have infinitely many. If many students took this course, we would expect, now this expect word is important because of this e to the x. We would expect an average grade of 2.8, which is between a B and C. So that would be my interpret. Okay, we can't have a mean if we don't have a standard deviation. So that's this next part. So standard deviation, I'm going to just fill this table out. Nothing's changed here. I have the probability of x sub 1, probability of 2, and then probability of n. Okay, so this doesn't change. So now we have this s squared. Now, if you remember, this value right here is our variance. Hold on real quick, y'all. Okay, sorry about that. So this s squared is our variance. And if you remember, our variance is going to be x1 minus our mean, and that is squared. Now this value is going to be times the probability of 1. And then we're going to take our next value, x sub 2 minus our mean squared times the probability of this second value. And we keep adding this up just like we would all the way through here. So this is our variance. So we can say var of x, this is the way you'll see it on the AP formula sheet, is the sum of the individual minus the mean squared times the probability of each individual unit. All right. So in terms of this summation funky formula, this is what it looks like. This is what it means. You take the value minus the mean, square it times the probability. Now this is the variance. Now this guy right here is our standard deviation. When we take the square root of the variance, we end up with the standard deviation. And so naturally, this is just the summation of individual minus the mean squared times the probability. Okay, so what we have here, it says, so for this example, for the Northwestern example up above, so this college class up above, find and interpret the standard deviation. So I'm going to do this by hand this one time. I don't think you would ever have to do this because it just takes too much time, but let me work through this really quick. So if I look at this, what I have is I know that my mean here, we calculated the mean at 2.8. So what my values look like is 0 minus 2.8 squared. This is if I got an F times 0.02 plus 1 minus 2.8 squared times 0.1. And this would be if I got a D. And I'm going to keep going. Oh, this is going to be 2 minus 2.8 squared times 0.20. And I'm going to keep going all the way to 4 minus 2.8 squared times 0.26. And if I did this, I did do this just to save time, what I get is that the variance equals 1. Now that is not normal. Normally you're going to get a number that's not 1. In this case, the variance is 1. So when I take the square root of both sides, I get the standard deviation is also 1. So what does this mean? We would expect the typical deviation from the expected letter grade to be 1 letter grade higher or lower. So standard deviation, so we would take our mean and we would add 1 letter grade higher, 1 letter grade lower. That's what that would tell us. Okay, now we can use technology to calculate the mean and standard deviation. You've done this. So when we calculate the mean and standard deviation, it's the same thing that we had before, but here's the problem that we have. When you go in and you do something in distribution, oh, sorry, I want to go to VARs, and I go to 1var data. So I go to stat, I go over and I look at 1var data. If I was to calculate everything, here's what I see. I see X bar, and X bar is my mean. And so if I know that X bar is my mean, and I have the standard deviation of X of 1 that's on here, these are the values. I went ahead and typed those in a minute ago. This is labeled as X bar is 2.8. What we see here is that we need this to be U of X equals 2.8. The calculator doesn't know if this data comes from a random variable or if this data is coming from just probability statistics where you just want to know what your mean is. So this tells us X is 2.8, not what the calculator gives, which is X bar equals 2.8. So be really careful. This tells us it is a distribution. This tells us it's just an average or a mean, okay? You can read this about what the AP exam says. Basically, it tells us you can use this little ... but that you have to show everything. You can't just plug it in your calculator, okay? All right, so let's work a problem here. So it says the U.S. Census collects data on the number of vehicles owned per household in the U.S. All right, so we're going to ignore very small percentages of houses that own more than 4 vehicles. So let V equal the number of vehicles owned by randomly selected households. So here's what we have. The probability distribution of V for recent year is given in this table. So number of vehicles. So I would say X equals the number of vehicles owned. All right, so this is my random variable. So Write the event the household owns one vehicle in terms of V. And I used X, but I guess I should be using V here. So what I would say is, what is the probability that V equals 1? Household owns one vehicle. And so when I do this, it's actually easier for me to use the complement of this because I can figure out what everything else here is. So if I look at these values, what I'm seeing is that my probabilities here, oh, I don't know why my decimals are messed up. Let me fix this real quick. These are my probabilities right here. So if I add those up, I have 0.09 plus 0.37 plus 0.14 plus 0.06. So this would equal 0.66. So if I add up everything that I have here, it's 0.66. So this would be 1 minus the probability of 0 plus 2 plus 3 plus 4. That's all the data that's given. And when I add that up, I would get 1 minus 0.66, which is 0.34, I think. Yes. Now, if you were going to go fill out this table and fill out this question mark, this is what you would do. You would say 1 minus all of these individual probabilities, and you would get 0.34. So all I did was justify how we get this value of 0.34 with the numbers. Okay? What is the probability that a randomly selected household owns at least one vehicle? So the probability that we own at least one vehicle. All right, so this is the same as the probability, 1 minus the probability of no vehicles. Now, we did this early in chapter 4, where we take 1 minus the probability of none, and the probability of none is 0.09. So we have a 91% or a 0.91 probability that a randomly selected household owns at least one vehicle. All right, we've got one more problem, and then we're going to get into some independent practice. So what this says is the game of Chuck-a-Luck has been around since before the Civil War. You place a bet on an integer from 1 to 6, and you roll three fair six-sided dice are rolled, and if one or more of the dice shows your number, you win. So the table here gives us our distribution, and X is the payout in dollars for a $1 bet on this Chuck of Luck game. Okay, so we're not going to make this histogram right now. We could make it, but we're not. We're just going to do the math. So it says calculate and interpret the expected value of X. Well, it doesn't give us a specific value. So really what we're looking for is the expected value of X is going to be, and I'm pulling these numbers from the table, it's going to be X of 0 times the probability of 0 plus X of 2 and the probability of 2 plus X of 3 and the probability of 3, and then X11 and the probability of 11. So when I put these values in, these are all of the different values. So let me plug this in my calculator real quick. And what I get here is 0.956. All right, so now let's talk about what we did. So what it tells us up here is that this is the payout in dollars. So this is the payout. So this is in dollars, and this is the probability that you're going to get that payout. So when I get to down here and I do the expected value, this actually becomes a number. This becomes 0.96 cents. So my interpretation, I'm going to just write in this, I'm going to write in the space that's up here because I have a little bit of room. So what does this mean? It says if many games were played, the average payout would be expected, or would expected to be expected 0.96 cents. So we say, but since the average player paid $1 to play, in the long run, and that's a very important phrase here, in the long run, that tells us that we're looking at a long time of gathering data. In the long run, the players lose an average of 0.04 cents in the game. Now, this interpretation here talks about two things. It talks about what this 96 cents means, but we have to go back and look in the context of the problem. For $1 bet on the game of Chuck-a-Luck. So it costs $1 to play, and that's what we say here. Since the average player paid $1 to play, in the long run, the player loses an average of 0.04 cents in the game. All right? So last thing here, and then we're done for today, and that is the standard deviation of this. So we know that we can find the variance, and with this variance, I'm going to have 1 minus 0.96 squared. It's not 1, it's 0, sorry. Our first value is 0, and the probability there is 0.579. And then I'm going to have 2 minus 0.96, and that is 0.347. And I'm going to go all the way up to 11 minus 0.96 times 0.005. And what I didn't do is I didn't include my little ... in there. All right, so I went ahead and cheated, and I wrote this number down just to save time in the calculator. And what I do is I get the square root of 1.70064. Okay. So now, I guess I probably shouldn't have done my square root yet. So I square root both sides, and this gives me my standard deviation of 1.30. Now, standard deviation has a unit. In this case, the unit is money. So my interpretation, if many games were played, the payouts would typically vary. There's our standard variation, would typically vary from the mean by $1.30. So again, understanding this standard deviation, that standard deviation is the variance from the mean. And you could actually even call out the mean being 0.96 cents. But it's important to say specifically, typically vary from the mean. Those are the key words that we need there. Okay? All right, you've got some individual worksheets that you can use to practice this concept now.